What is the radius of convergence for 4 times 1 minus x to the power 2n divided by n times 9 to the n? We have a couple of options. Negative 8 to 10, we include 10. Negative 8 to 10. Negative 2 to 4, include the negative 2. Negative 2 to 4. And negative 5/4 to 13/4. We have an answer? Sorry, what? D? Are you sure you want to go with D? Okay, that's right. D is the correct answer. Negative 2 to 4. All right, so what's the process? Well, whenever you're asked for interval of convergence, there's always 2 steps. And they like interval of convergence type questions. Sometimes they like radius of convergence type questions. We'll talk about that. So step 1 is you've got to work on getting most of it. And you use either the root test or the ratio test. You can use both. I would say bias towards the root test. Unless you see a factorial, then you say, got to go with ratio test. So we're thinking of the whole thing, including the x, as our term in our series that we're adding up, our a sub n. So take the limit as n goes to infinity, absolute value, nth root. And so we say, okay, we'll do that. 4 to the 1 over n, 1 minus x to the power 2n to the 1 minus n. And the 1 minus x is the only thing that needs the absolute value. Everything else is positive. N to the 1 over n, 9 to the n to the 1 over n. And then you just say, well, okay, so things like to the 2n power to the 1 over n power just becomes squared. To the n to the 1 over n becomes just 9. You know a couple of rules. N to the 1 over n goes to 1. A constant to the 1 over n, that goes to like 4 to the 0. That goes to 1. There's no ambiguity there. So you end up with absolute value 1 minus x squared over 9 is less than 1. Now, be careful. This square, you have to pay attention to it, because it will change your answer. If you forgot it, you would have guessed B. And now at this point, we're working on figuring out the interval up to the endpoints. So, okay, move the 9 across, take the square root. Note that absolute value of 1 minus x is the same as absolute value of x minus 1. We like to write it where there's a 1 in front of the x. So we think of x minus a. That's how we like to write it. And so we get an interval from negative 2 to 4, but we don't know the endpoints. So now you have to test the endpoints. They might both be in, they might both be out. Maybe one's in and one's out. You don't know until you check. So check the endpoints, which means you plug in negative 2, you plug in 4. In both cases, you get a harmonic series, which diverges, so we don't include either endpoints. And that gives our answer. Okay, so that's the process. You might notice I made a note here. Don't worry about where you start. Convergence doesn't happen at the beginning. So don't worry about your start. It's what happens at the end, towards infinity. So don't get distracted by your starts. One other question before we go. How much did this 4 affect our final answer? And did it affect our final answer, I suppose I should ask? It didn't. Is that surprising to us, or should we sort of say, constants won't matter? Constants don't matter, yeah. No matter whether you're doing the ratio test or the root test, constants essentially vanish in one way or another. So it's not constants that will determine anything. So we don't have to pay much attention to them. We, of course, should write them down, but we know ultimately they should go away. Okay, any questions on this one? All right. Well, thought for the day, and I suppose I'll preface it before I put it up. I did my graduate work in San Diego at a school out there, UC San Diego. And we had the Geisel Library. So I thought, I I should share a thought from Mr. Geisel. Now, who is Theodore Geisel? Well, also known as Dr. Seuss. So, it's actually a really interesting building. You probably have seen it show up from time to time. They use it for science fiction shows and films. All right, so, from Theodore Geisel. Today you are you. That is truer than true. There is no one alive who is youer than you. I think Dr. Seuss had a lot of interesting things to say. And I like this. Sometimes when you're in a large class, it can be easy to feel like you're just a cog in a machine, and that, your identity doesn't matter much. But we want each of you to succeed. We know each of you is your own person. You have different backgrounds, different strengths, and different weaknesses. And that's okay that you come from different places. And you'll have different journeys. But we want you to do well. We want you to be your best self. All right, now, what are we doing today? Goals for today. Okay, well, a lot to write down, but don't worry, most of it is review. We have some additional practice for interval of convergence. We already worked through a problem with our warm-up. And remember, it's basically just 2 steps. Figure out your radius, work on your endpoints. We'll do a little bit of additional practice with rewriting using geometric series. And I want to start to get into the mindset of how do you put things into a mold? Recognize, there's a mold here. How do I rewrite? Because that's going to be a theme coming up in the next few lectures. We'll talk about calculus of power series, and essentially what you think should be true is true. And so think of it as I've got a big polynomial, because that's how you should think of power series. They're like a big polynomial. It just so happens they may not always make sense, but where it makes sense, okay, I'll do what I think I should do. So if I'm thinking of taking the derivative of a polynomial, I say, okay, I'll just take the derivative term by term. If I'm thinking of doing the integral of a polynomial, I say, okay, I'll just do the integral term by term. And that's what you do. So to take the derivative of a series, you say, okay, imagine pushing the derivative inside, and you take the derivative of x minus a to the n comes down x minus a to the n minus 1. Similar thing with the integral, or if you like the antiderivative, you can push the integral in, and you get the integral of x minus a to the n. That's x minus a to the n plus 1 divided by n plus 1. Work term by term. This is a very common idea. You'll hear it again and again. In fact, it says it right here in the next part. We can talk about combining series. You can add series. Well, if you want to add polynomials, how do you add polynomials? What's the mindset? What do you do? You find the powers that are matched and you add coefficients, right? Well, that's what you do with series. You can scale polynomials. You can also multiply polynomials, which involves expanding or doing foiling. And it works with series. So basically, just remember, when in doubt, work term by term, and it will pretty much always work out. All right, so that's what we have for today. A lot to do, but that's all right. Oh, there was this note about calculus of power series. As long as we're in the interior of our interval of convergence, life is good. The endpoints, that can get interesting. You have to check. You have to check. All right. Well, let's do a problem. Find the radius of convergence for the following sum. N equals 3 to infinity, n to the power 2n, n factorial, x plus 4 to the n, divided by n squared times 3n factorial. All right. Now let's be careful here. We are after the radius of convergence. So what aren't we going to look at? The endpoints. So not every problem has you check endpoints. So make sure you read carefully. And if it says find the radius, you say, okay, once I found the radius, I stop. If it says find the interval, it's like you got to make sure to find the endpoints. You want to follow instructions because they're very picky about that. They seem to like mark people down when they don't follow instructions. That's very, very rude. But okay, so we're after the radius. What test are we going to use? Why will we use it? Ratio test. What's the clue that this is a ratio test? Yeah, the factorials. Once you see factorials, at this point in time, it's pretty much a ratio test coming into play. All right, so what do we do? Well, think of this whole thing here, including that x plus 4. All together, this is our a sub n. So, ratio test, we're going to take the limit as n goes to infinity of absolute value of an plus 1 over an. So that's where we're heading. All right, now in terms of absolute value, what's the only piece of an that the absolute value has any effect on? Yeah, the x plus 4. So I'm going to just push the absolute value in and say that x plus 4 becomes absolute value of x plus 4. And then I'm not going to worry about absolute value other than that. So just to let you know. All right, step 1. I'm going to write an plus 1, which means everywhere there's currently an n, put n plus 1. All right, so n plus 1, 2 to the n plus 1. N plus 1 factorial. Absolute value x plus 4 to the n plus 1. Divide by n plus 1 squared times 3 times n plus 1 factorial. Okay, so there's our a n plus 1. And then we divide by an. And to divide by an, it's the same as to multiply by the reciprocal. So I'm just going to do that. N squared 3n factorial, n to the 2n, n factorial, absolute value of x plus 4 to the n. And there's our 1 over a sub n. All right. Now, we want to get to the point where we can get some nice cancellations going on. And in particular, because of the factorial. Now, let me just make a quick comment here. This n plus 1 to the power 2 times n plus 1, that's really the same as n plus 1 to the 2n times n plus 1 squared. Because that 2 times n plus 1 is 2n plus 2. And when I have addition upstairs, I can separate it as multiplication. All right. So I make that comment just because I say, aha, we get some quick cancellation. Now, factorials. What do you do with the factorials? Do you remember the idea? Pull terms off, right. Factorials, again, we can just repeat this with like n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. And eventually you say dot, dot, dot. But the punchline is, it's really just one more term than n factorial. So it's like, hey, if I would think of n plus 1 factorial, I can just think of it as the first term, pull that off, and then the rest that's left is still factorial. So we have I'll do this n plus 1 factorial. That's n plus 1 times n factorial. 3n plus 1 factorial. Well, that's the same as 3n plus 3 factorial, if I multiply the 3 through. Pull off terms. And you just keep pulling off until you have something to cancel. So it's like, well, if I pull off the 3n plus 3, then I'd be left with 3n plus 2. And that's not ready to go yet, so I pull off the next, keep going. Pull out 3n plus 2, I have 3n plus 1. Nope, not there yet. pull off 3n plus 1, I'm left with 3n. And then like, perfect. And then I'll just put the rest of those into the factorial. So just pulling off at the beginning. Okay. What are we taking into account? We've taken care of the factorials there and there. Okay. Well, we need the n factorial downstairs. Okay, that takes care of that one. We need the 3n factorial upstairs. That takes care of that. We should write the n squared. So we'll write that. What's left? What haven't we taken account? Yeah, we have n plus 1 to the 2n, n to the 2n. We'll put those together. And they're kind of separate. So we'll write those together. They're both to the 2n power. So n plus 1 over n to the 2n power. Okay, that takes care of those terms. Anything left? Yeah, those x plus 4s. And when you look at these, what can we do? We have n plus 1 of them upstairs, n of them downstairs. Their powers combined. That leaves us with a single one upstairs. All right. Well, our work with our factorials gets us to the place where we get cancellation. So there's no more factorials involved. So we really have 3 pieces. We just have to say what happens to each piece. We'll start towards the back. As n gets big, what happens to this absolute value of x plus 4? It's constant. There's no n involved. So it just stays as absolute value of x plus 4. So that's cool. All right. Moving a little bit back. This n plus 1 over n to the 2n. What happens to that? Or maybe what's another way to write this? Okay, so someone said, hey, this looks like 1 plus 1 over n. Now you might say, why are we doing that? Because we might look at our equation sheet and say, hey, on our equation sheet, there's this handy dandy limit that says 1 plus t over n to the nth power is e to the t. So if you think, hey, maybe if I can use that, I got to make it look like the limit. Okay, so if I want it to look like this limit, what should I do with my exponent? Because my exponent is currently 2n, but what's another way to write 2n? N squared, right? Because multiplication, I can think of it as successive powers. 1 plus 1 over n to the power n, okay, goes to e. So the whole thing goes to e squared. Don't forget that square. So just the inside part goes to e, so the whole thing goes to e squared. All right, now, this first part, what do you see? Yeah. Someone said equal powers, top and bottom, and in particular, it's polynomial over polynomial. So when you have polynomial over polynomial, you check the degrees. The degrees are the same. If the degrees are the same, what do you need to look at? The leading coefficients. What's your coefficients of your highest power? Now, there's a couple ways to do that, but I think if you say, I look at the highest power and what's your coefficient? So the highest power is a cubed. Upstairs, what's the coefficient of n cubed? 1. So coefficient of n cubed. Upstairs, it's 1. Downstairs, if you multiply this out, what's the coefficient of n cubed? 27, right? Because you have 3n times 3n times 3n. So this is going to go in the front to 1 over 27, which tells us what? Well, it tells us that our limit, when we put this all together, is e squared divided by 27 Absolute value of x plus 4. Okay. Now, we've done a lot of work. We're really close, but we're not quite done. When we're applying the ratio tests, we want convergence. What needs to be true? This limit should be less than 1. All right. Now, we have another thought. We're full of them. We want to write it in the form x minus a less than r, where a is your center and r is your radius of convergence. So, how do we get from this to that? Multiply the 27 over e squared on both sides. So absolute value of x plus 4 is less than 27 over e squared. Now, what's the radius of convergence? Because we've written in the right form, so we should be able to mark it. 27 over e squared. So this is your radius. Quick question. We didn't seem to use it. What is this telling us? This plus 4, because it didn't affect the radius. What is it affecting? It's your center. Now, if the problem, sometimes they'll say find the center and the radius, then this, you say, aha, the center is from this part here. But in this case, it was just after the radius. Now, on a side note, we're done with this problem, but you may say, can we never do a root test with factorials? Well, the problem is you need to know a little bit more about factorials. I'll mention that we do know about factorials. When I say we, I mean mathematics knows. We haven't yet done it yet, but I'll just mention it in passing. It turns out that n factorial is approximately square root of 2 pi times n over e to the nth power. You know, I'm sure you've often wondered this. And so if you know that, then you can start saying, aha, do things like interval of convergence. Then you have a chance. But without knowing a little bit more about factorials, interval of convergence is pretty hopeless for most problems involving factorials. All right. Oh, I'm sorry, I moved quickly away from this. Any questions? You don't need to remember that. That's just a fun aside. A bonus fact from coming to today. From the ratio test and checking endpoints, the series, the sum n equals 0 to infinity of a sub n x plus 4 to the n, has an interval of convergence from -9, including 9, up to 1, but not including 1. And then there's two questions. What's the limit as n goes to infinity, an plus 1 over an? And a second question, what is the interval of convergence of the power series, the sum from 0 to infinity 2n an x minus 3 to the n? Now, do we know what an is? We do not. So can we answer this question? Hopefully. Let's see where we can begin. Maybe we'll start here. Let's graph this interval. So we have -9, and we're including that, up to 1, but we don't include that. All right, and we're saying we definitely converge in between, and we definitely diverge outside of that. So, what can we say? Well, we can certainly do a couple things. We can find the center. How do you find the center? Oh, it feels like I'm asking a trick question. I'll give you a hint. There's two ways to find it. Oh, you're being torn. Oh, which way does Steve want? Which way does he want? So where's the center? -4. All right. Method 1 to get it. The center is the middle point between -9 and 1. So just say what's halfway between -9 and 1, add them up, divide by 2. Another way you could get it, look at your expression. This is x minus -4. And so when you have a power series, x minus a to the n, a is your center. So -4 is your center. Okay, so now we have that -4 is our center. Next question. Do we know what the radius of convergence is? Can we find that number? 5. Where did that come from?
Distance from both ends.
Yeah. How far you have to move. So our radius of convergence is 5. Okay. Can that help us with this question? What does this look like? It looks a lot like a ratio test kind of thing. So let's apply a ratio test. Now, if we do a ratio test with this series, as if we were saying, let's find our radius of convergence, it's our limit as n goes to infinity. We would take the absolute value, an plus 1, x plus 4 to the n plus 1, divide by an, x plus 4 to the n. Now, this becomes the limit as n goes to infinity of absolute value of an plus 1 over an times x plus 4. Now this doesn't really change. That's just x plus 4. And remember that we want this to be less than 1. So, it says, we need to limit as n goes to infinity, an plus 1 over an times absolute value of x plus 4 needs to be less than 1, or absolute value of x plus 4 has to be less than this limit as n goes to, 1 over, limit as n goes to infinity, an plus 1 over an. But now, a question. What is this number and why? 5. Good. You cracked the code. There's good pieces of advice. If you're ever taking a math class, and you're currently enrolled in one, then the answer tends to be one of 3 possibilities. The 0, 1, or it's probably written down somewhere. In this case, 5. This is the radius. That's what should be here. So if 1 over this limit is 5, what's the limit? 1/5. So the answer to part A is the limit as n goes to infinity of absolute value of an plus 1 over an is 1/5. And in particular, this is the limit that helps to determine the radius. So, all right. So that's part A. Part B. What is the interval of convergence of the power series, sum n equals 0 to infinity 2n an x minus 3 to the n? Now, to help us answer that, I'm going to skip around a little bit, or maybe jump back and say, you have this original sum. I'm going to replace it, the sum n equals 0 to infinity an times something to the nth power. And I'll be a little bit vague here. So I have a box. Now currently, what's our box? X plus 4. Okay, and we know that this will converge. So when I put in x plus 4, that's our box, which is x plus 4. When will that converge? So if I put in x plus 4, what does the interval become? -5, including -5, up to 5, but not including 5. So the form says this sum, whatever you put in here, will converge as long as what you're putting in it is between -5 inclusive to 5 not inclusive. Yes? No? Maybe? Perhaps. Why do I say all that? Well, let's look at this sum. What's another way to write it? Well, you have your an, and then you have 2 to the n, x minus 3 to the n. So that's 2 times x minus 3 to the n. What does that tell us? This, 2 times after the x minus 3, is what we're putting into the box. The age-old question. What goes into the box? So what do I do with this 2 times x minus 3? I put it into there. So this will converge for -5 less than or equal to 2, x minus 3 less than 5. What's the last things we need to do? Divide by 2, -5 halves less than or equal to x minus 3 less than 5 halves. Now add 3. -5 halves plus 3 is a half. 5 halves plus 3 is 11 halves. So our answer is it will converge for 1/2 less than or equal to x less than 11 halves. So this is testing our can we work with series. And in particular, can you think about what's in the box? You have a mold. What goes into the mold? And can you manipulate? All right. This is a very different type of problem than the ones we've done otherwise. So it's okay to have questions. If you have questions, let me know. Or you can meditate and ask questions later. Help hours is good for that. Okay, let's jump to calculus of power series. So, the good news is, what we would like to be true is true, which says that you work term by term. And so if I want to take a derivative of a power series, I can pass the derivative through the sum. If I want to do an integral of a power series, I can pass the integral through the sum. Now there's some technicalities here. I don't want to say, oh, this is trivial, this is obvious. It's not. And the issue comes down to you have multiple limits in play. Integration or derivatives involves limits, but so do series. They involve limits. And it's a question of when are you allowed to sort of fidget with your limits. And that took math a long time to figure out. And one of the things I figured out is like, well, as long as you're absolutely convergent and you're in an interval, life is good. But the good news for us is that when we have an interval of convergence, we are absolutely convergent on the inside of the interval. Now the endpoints, you don't know. So you just say, look, I'll carry it through, and then I'll see what the endpoints do. The endpoints may not be converging. You do something, and suddenly they do converge. Or vice versa. So you don't know. But the good news is that when they do converge, you get what you expect. All right. So what's the main takeaway? Well, one thing we can do is, if I want to bring an n down, I can take a derivative. So that brings the power down. If I want to get an n plus 1 in the denominator, if I want to get something downstairs, I can integrate. So now we have an example. We're given this sum. The sum from 0 to infinity, x to the n, and it's 1 over 1 minus x. So it's our classic geometric series. We've gotten really good at that. And now we're asked to do the following. Find a rational function for the sum 0 to infinity n x to the n. Okay, let's talk about what doesn't work. Because there's something that's very tempting. So, just warning, this doesn't work. Here's a thought process that some people have. Let's write it down, and let's talk about why it doesn't work. You say, I know what happens with x to the n. Here's an n. Let's just factor it out. And then I have the sum of x to the n, so that's good. So this should be n over 1 minus x, right? Is this correct? Well, I've already told you no. But I'll still ask the question, is this correct? No. Why not? I do want to be clear here, because I'm going to do something that feels a little similar in just a moment. So I want to be clear why this doesn't work. N is changing. That's a great answer. Yes. N is not one thing. N takes on infinitely many values. Sometimes it's a 7. Sometimes it's a 26. Sometimes it's 142. It's a lot of different things. And so you can't treat it like it's a constant thing. So this is where it breaks down. You can't pull out things which are dependent on n. So that's just off the menu. So n is changing. Great answer. Great answer. Okay, so that's not what we're going to do. So you say, okay, what can we do? Well, I have an x to the n. What can I do to x to the n to put an n downstairs? Would the integral of x to the n put an n down? Well, when I say downstairs, I don't mean downstairs. I just mean in front. Take a derivative. So let's start with this. We have 1 over 1 minus x. That's the sum. 0 to infinity, x to the n. So we'll take a derivative. And when I say take a derivative, we'll take a derivative of both sides. So if they agree in the interval of convergence, the derivatives have to agree in the interval of convergence. So we have to take two derivatives. What's the derivative of 1 over 1 minus x? Or if you want, what's the derivative? Which derivative do you want to do first, the left or the right? I get a feeling like I don't want to do either of these. So 1 over 1 minus x, you can think of that as 1 minus x to the minus 1 power. So then the minus 1 comes down. 1 minus x to the minus 2 power. Anything else? If you're taking derivative? The inside. Derivative of the inside. Chain rule. Derivative of 1 minus x is minus 1. So you have two negatives. So you end up with 1 over 1 minus x squared. So that's the derivative of the left-hand side. Cool. Now, the right-hand side. Well, we're taking the derivative, and the moral says you can take the derivative term by term. So I say, well, this is the same as the sum from 0 to infinity of the derivative of x to the n. So what's the derivative of x to the n? N x to the n minus 1. Okay. We're like, yes, this looks pretty cool. But we wanted nx to the n. We currently have nx to the n minus 1. It was so close. So close. Why do you do this to us? Sorry, what?
Right now it's n times x to the n over x technically, right?
Okay, yes.
So you could pull 1 over x out.
Right. Yes. And now, so there's a suggestion we can pull 1 over x out. I'll phrase it in a slightly different way, but in an equivalent way. You have the right idea. I can multiply by x in. But we can put something in and we can pull something out. Why can we pull? Well, okay, so I'll follow through your suggestion here. 0 to infinity and x to the n over x. And the idea is like, hey, let's pull this to the outside. Why can we pull an x out, but we said we can't pull an n out? X isn't changing. Regardless of what n is, x is x. Now, the way I can achieve that effect of pulling an x out and then moving it across is I can just say, let's multiply both sides by x. So times x on both sides. So we have x divided by 1 minus x squared is, and I'll go through this, I'll think of multiplying on the outside, but now push it in, and you do it term by term. You say, well, every term has an extra x, so you get n x to the n. All right. Now, what's the next thing we need to do? I know, this is a tricky step. It's a hard step. So what's our next step? Yeah, we box our answer because we're done. That's it. X over 1 minus x quantity squared. So by doing some calculus, we could find this series. All right, I want to make sure we have enough time to finish this one. I don't know why, but this one appeals to me. Find a power series for the function arctangent of x, centered at x equals 0. And what is the interval of convergence for this power series? Okay, so arctangent of x seems pretty hopeless. Well, what are some things we know about arctangent? Put on our calculus hats. What are some things we know? Now keep in mind, we're after something with series. And at this point, how many series do we actually have that we can say, aha, it does this? It's a very short list. It's a really short list. It's a list that's one thing long. So that's going to help us. So if we're after a series, right now, the only series we have in our back pocket is the following. N equals 0 to infinity of something to the nth power is 1 over 1 minus something. Now, here, let me be a little bit more specific with the question. Is there something about arctangent that has this flavor? 1 over 1 minus something. What? The derivative. Oh, nice. Nice. Okay, so the derivative of arctangent of x, well, that's 1 over 1 plus x squared. That definitely has the flavor of 1 over 1 and then stuff. Now, we have to fit the mold. So we have to write 1 over 1 plus x squared as 1 over 1 minus something. What goes into our mold? What goes into the box? Negative x squared. Right? To get a plus, you can subtract the negative. Now that we have the right mold, we can say, hey, the derivative of arctangent, that's our sum, 0 to infinity, minus x squared to the n. And we can write that as 0 to infinity of negative 1 to the n, x to the 2n power. Okay, so good news. We know how to write the derivative as a series. But I didn't want to say what's the derivative of arctangent as a series. I said I want an arctangent as a series. So how do I go from the derivative of the arctangent to arctangent? You integrate. So you say, hey, arctangent is the integral of the derivative of arctangent. That feels very fundamental to know that. So that's the integral of the series. But how do we do these integrals? We pass the integral through, term by term. So this becomes the sum n equals 0 to infinity. Negative 1 to the n will be negative 1 to the n. That doesn't depend on x. We're integrating with respect to x. And I'll go ahead and write it as integral of x to the 2n dx. So move the integral in. What's the integral of x to the 2n? X to what power? Two n plus 1, and then divide by your new power plus c. How do you find c? You do have to find it. Answer, plug in a convenient point. At x equals 0, what happens? You get arctangent of 0. Arctangent of 0 goes by the name 0. When you plug in 0 into your series, what do you get? 0 plus c. So c is 0. So our power series for arctangent of x is the sum from 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And we don't have time, but I'll just say we now get the endpoints included as well. So negative 1 to 1 is the interval.